Welcome back to part 12, Dents and Gouges. This is episode 1.2 or part 2 of an earlier video we did. And this time we're going to look a lot more closer at API 579 and 2021 version. And I'm not going to deviate because recall last time I deviated because there was a lot of interesting work that the pipeline people have done over the years in API and in ASME, and it's some very applicable, I thought, to dent analysis. There's actually quite a bit also research has been done on gouges and things like fatigue, and if there's any interest, I can provide a presentation on that in the future. So that's up to you. So gouges applicability, it'll be the first thing that we'll look at, level 1 and 2. The previous video, we already looked at level 1 and 2 dents. Secondly, we're going to look at the dent and gouge combinations and looking at the level 1 and 2 assessments. Recall, level 1 is a very basic one. It's designed for 10 minutes or so, 15 minutes to go look at it on paper. Level 2 is, at least a half a day's work to look at that, depending on the complexity, of course. And when to use the level 3, which requires an expert to look at, and there's some advice on that. 12.2 talks about the applicability and limitations. And let's talk about gouges and what box the definition of a gouge fits into doing an assessment. So a gouge, it refers to an elongated local removal or relocation of material from the surface of a component caused by mechanical means that results in a reduction in the wall thickness, more of like a substantial. I mean, by definition, that could also be a scratch as well. So let's continue that because there is some differences, and I would say it's an appreciable wall thickness. Next is the length of the gouge must be much greater than the width, and the material may be cold worked in the formation of a flaw. Secondly, it's similar to a groove that's found in part 5. In some of the future examples, we will see that we go back to part 5 and do an analysis, and equations are very similar, which is quite handy so that you can you can follow very similar procedures. So it's mechanical damage, and what happens is that you have a work hardened layer that's created as we gouge the surface, because in order to plastically deform the part and remove material, then we'll leave some hardened material in the parent material behind. And so what that means is when you're doing repair of any gouges, you should be removing that work hardened layer on the parent material, and that's one of the conditions for doing an assessment. Lastly, the localized work hardening makes it classified similar to denting. Has, of course, we talked about last time, we have dents, we have gouges, and then we have a combination of a dent and a gouge. And in figure 12.3, it describes the dent gouge combination. So here's in dotted line is the original configuration, and the depth is defined as to the top of there, and then the top of the ridge, and then the gouge is shown below that ridge, and T min is described, in terms of the difference, that's the retained material in it. So so that's basically it there. We look at applicability. There's two levels that we'll look at. for dent and dent gouge combinations. They actually put dents and dent gouge combinations together because the procedures are quite similar. So the original design, first question is the original design criterion to a recognized code? And we have earlier videos in part 1 about the recognized codes. That would be, for example, was the piping system built to, CSA Z662 or B313, or was it part of ASME Section 8 Division 1? Secondly, does the material have sufficient toughness? And there's some criterion for that, because if, for example, if we're operating colder than the minimum design metal temperature, then we could be in the brittle phase of the material and we could have a fracture. So this mechanics assumes that the material has some ductility. Thirdly, see part 3 if uncertain. And then it says here, if during operation subject to embrittlement caused by temperature or hydrogen performance, then or hydrogen inclusions and that kind of thing, then you need to perform a level 3 analysis, which is a very detailed analysis. And that analysis is described in Annex 2B of 2021 edition. Now you need to consider the fact that cold work damage increases susceptibility to cracking, because when you work hard in the material by gouging it, you make that surface harder, and when it's harder, the ductility tends to drop for steels, and basically you can have more chance of cracking. Here in 12.2, first of all, there's a rule that says that the cylindrical shell geometry must meet the following criteria. First of all, DO, defined as the outside diameter, must be between 6 NPS and 42 inches outside diameter. And the thickness RD, which is a uniform thickness away from the damaged component, it should be between 5 millimeters and 19 millimeters, which is up to 3/4 of an inch. Then they go ahead and they say D over TRD, the ratio of the diameter to the thickness ratio is between 23.6 and 80, and the background behind that is that it's using thin wall pipe stress theory. It's just they want to make sure that you're not trying to evaluate, make a gun barrel which is like inches thick, and the diameter ratio would be much different. So that's the reason why they have that criterion. More on dents and dent gouge combinations. The analysis must be done for level 1 and 2, assuming that the component is subject to internal pressure only. So anything like a supplemental load, such as wind load, which would cause bending, for example, any kind of mechanical load, such as weight or bending on a pipe rack, for example, causing the pipe to bend between the supports. Those are considered to be negligible, which isn't too bad of an assumption, actually. There's also conditions on the material properties. The minimum yield stress SMYS applies to the static assessment if it's less than 70 KSI or 482 MPa. Also, the ultimate tensile stress, the UTS, applies to fatigue applied to a fatigue assessment must have a ultimate tensile strength less than 710 megapascals or 103 KSI. The assessment procedures only apply to isolated dents, and the dent gouge combinations. Like for example, it can't occur in large clusters of them. And then here's some spacing rules. So the spacing must be greater than 2 times the LMSD. Where the MLSD refers to the dent spacing to the major structural discontinuity. So that could be also dent spacing to, for example, like a circ weld on a line or a longitudinal weld, or a circ weld, or you can also call it a girth weld. For dent and gouge combinations, gouge orientation shall be in the axial direction. Okay, that means longitudinally along the length of the pipe. Circumferentially oriented gouges in the dent gouge combinations require a level 3 assessment. That's because the hoop stress is much higher than the longitudinal stress, and so there's more to be involved with that when it's not just a simple calculation. Specific for gouges, a condition. The material toughness satisfies all the assessment criteria that we meant for that. It can't be a brittle material as described in part 2. We use the level 1 and 2 assessment of part 5, including the applicability and limitations of part 5 in the procedures. 2 has a few more conditions for gouges and fatigue, a level 1 assessment. Basically, it says it's applicable if not in cyclic service with the following exceptions. If the cycles are less than 150 cycles, and that can be, pressure or temperature variations during changes in operation throughout its entire operating life, or secondly, it satisfies the screening procedure in Part 14, fatigue. For level 2, there's a few information here about the conditions. If the component is in cyclic service and the fatigue analysis is provided, then a permissible number of cycles shall be determined. Second thought, if the pressure cycles are complex or other forms of cyclical stress are concurrent, then a level 3 assessment is required. Applicability of level 3 procedures, which we recall is the most intensive calculation requiring expert engineering specialist skill, abilities and experience. Some examples include the component geometry that does not satisfy the level 1 and 2 requirements. So for example, if it's on a reducer or a branch. Another one is the component loading condition combinations can include internal pressure, external pressure, supplemental loads like wind, earthquake, and thermal loads. So recall from the levels 1 and 2, that was not permitted. You had to use pressure only, and assuming that the other load combinations were negligible. The component material meets the level 1 and 2 requirements. You have to go back to level 1 and 2 and make sure that, for example, the the toughness is there in that component. You can't do the assessment, or you're not permitted if the material is considered, brittle. So recall that with gouging, when you basically remove material from it mechanically, you'll have this very thin, hard layer that must be removed in order at any condition, whether you want to continue service or not. That hardened surface must be removed, and that's part of the conditions of the standard. Continued. So components with a design based upon proof testing. Um, Example, piping, tees, reducers produced in accordance to 16.9. They require more detailed analysis. The complex cyclic cases, again, where it was not permitted in 1 and 2, you can do it for these cases. Recall that we have some videos on fatigue and looking at how cracks can grow and the different complexity of cyclical cases. You can invite you to have a look at the video in our library. Continued. The components that are operating in the creep range, level 3 is required. Components that are closely spaced dents and gouges and or dent gouge combinations, level 3. Recall earlier with 1 and 2 there was spacing requirements. The analysis could only be done if the gouge was in isolation, which is not always easy. If you look at the diagram in the background here, you can see that there's always a faint one and a larger one. That typically what you see, there's a faint one there, and then that's a deep one. So it's always gray.